Today in this video we are going to discuss about Maclaurin series using differentiation and integration. But before that, what we have done in the previous video, we have done in the previous video that the Maclaurin series, how the function can be represented in power of x, and that is we have done in the previous video. Also we have represented graphical representation of the respective functions like sin x, cos x and so on. And today we are going to discuss about the different forms based on the Maclaurin series and using the differentiation and integration. So here, this is the first form we are going to use. So this is the first form, that is 1 divided by 1 plus x minus x plus x square minus x cube plus and so on. And that form can be derived using the Maclaurin series expansion. And similarly, we will also use this form. And this is the standard forms which are obtained from the Maclaurin series expansion. And this is the binomial expansion, and that we will use later on. So here, this is the first question. Using binomial series, find series expansion of the sin inverse x and hence find series expansion of the cos inverse x. That means what we are going to consider. We want to express sin inverse x in power of x because we are using the Maclaurin series, but not exactly Maclaurin, but we will use the binomial expression, and based on that we will use the derivative and integration, and finally we get the final answer. So here first f of x is equal sin inverse x. And here first derivative will be 1 divided by 1 minus under root 1 minus x square, that can be written as 1 minus x square raised to power minus 1 by 2. And this is our binomial expansion and we are using this form. So first we replace x by minus x square. So here we get f dash x is equal 1 plus minus 1 by 2 of minus x square plus and so on. After representing all these values, that means x is replaced by minus into x square, we get this form, and that is first derivative. But what we are using here, integration differentiation concept. So first we integrate with respect to x. So we get integration of f of x into dx is equal integration 1 divided by under root 1 minus x square into dx is equal integration 1 plus x square by 2 plus 3 into x raised to 4 divided by 8 plus and so on, and we are integrating with respect to x. So here what we get? We know that integration differentiation both are antiderivative. So integration of f dash x into dx, and that is going to be function f of x because derivative and integration both are antiderivative of each other. So integration of 1 divided by under root 1 minus x square into dx, and that is going to be what exactly sin inverse x. But again if we integrate with respect to x, so we get x plus x raised to cube divided by 3 into 2, that is going to be 6. So after simplifying we get here sin inverse x is equal x plus x raised to cube divided by 6 plus 3 divided by 14 to x raised to 5 plus and so on, and integrating constant plus c is there. But if we put here x is equal 0, so what we get? Sin inverse 0, that is 0. But if we represent all these x is equal 0 on the right hand side, so what we are going to get? C is equal, that is 0. And final, that will be the sin inverse x is equal x plus x raised to cube divided by 6 plus and so on. And but we know that c is equal 0, so this is the final representation of the sin inverse x. And suppose you want to find here cos inverse x. So in that case also you can find, but this is our standard formula, sin inverse x plus cos inverse x is equal pi by 2. So from this we can write cos inverse x is equal pi by 2 minus sin inverse x. But already we have the expression of the sin inverse x. So when we replace it, so we get here cos inverse x is equal pi by 2 minus x raised to cube divided by 6 minus 3 divided by 14 to x raised to 6 and so on, and that will be the expression of the cos inverse x. But suppose you want to make a bracket for the sin inverse x, so in that case what you can write pi by 2 minus in bracket x plus x raised to cube divided by 6 plus and so on. But when you expand this bracket, so in that case you will get all the terms will be negative except pi by 2. Now, this is another question. Find the Maclaurin series of the tan inverse x. So again, we are going to use your derivative integration concept. But we know that derivative of the tan inverse x is what exactly 1 divided by 1 plus x square. But we know that expression of the 1 divided by 1 plus x, that is 1 minus x plus x square minus x cube plus and so on. But now we replace x by x square, so we get here that is 1 divided by 1 plus x square is equal 1 minus x square plus x raised to 4 minus x raised to 6 plus and so on. But now it is required to integrating with respect to x, and then we are going to get tan inverse x. So now we do simply integration on the both the side with respect to x. So we get here f of x is equal x minus x cube by 3 plus x raised to 5 by 5 minus x raised to 7 by 7 plus and so on, plus integrating constant c. But now our target is to determine the constant c. So how we can determine? So for that you have to just consider x is equal 0. So f of 0. But what was our function f of x? That is tan inverse x. So when we put x is equal 0, so we get tan inverse 0, that is only 0, and equal to 0 plus c. So ultimately we get c is equal 0. So after putting c is equal 0, we get f of x is equal x minus x cube by 3 plus x raised to 5 by 5 and minus x raised to 7 by 7 plus and so on, and this is the expression for the tan inverse x. So this is another question. Now prove that tan inverse of under root 1 plus x square minus 1 divided by x, and that is equal to 1 divided by 2 into x minus x cube by 3 plus x raised to 5 by 5 minus and so on. So for that LHS is equal RHS, that is we are going to show that. But how we can? So for that you have to consider LHS or RHS. For our simplicity we are going to consider on the LHS, that is tan inverse of under root 1 plus x square minus 1 divided by x. But whenever you are going to using substitution method, so whenever you look at the trigonometric function 1 plus something, so we will use x is equal tan x, tan theta or the cos theta, or whenever we have 1 minus something, so in that case something can be written as sin inverse, sin x or cos. So in that case respectively you can consider, but in this particular question we are going to consider x is equal tan theta. So we get here under root tan inverse of under root 1 plus tan square theta minus 1 divided by tan theta. Already we have considered x is equal tan theta. But when we simplify 1 plus tan square theta, that is going to be sec square theta. But under root is there. So we get sec theta minus 1 divided by tan theta. But now sec theta can be written as 1 divided by cos, and tan theta also can be written as sin divided by cos. But after simplifying you will get tan inverse of 1 minus cos theta divided by sin theta. But we know that the formula for 1 minus cos theta, that is 2 times sin square theta by 2, and sin theta can be written as 2 times sin theta by 2 into cos theta by 2. But when you simplify, so one sin will be cancelled out, also 2 will be cancelled out, so you will get sin divided by cos, that is tan theta by 2. But tan inverse of tan theta by 2, and that is going to be what exactly theta by 2. But what was our theta? But x is equal tan theta, so we can represent theta is equal tan inverse x. So we get LHS is equal tan inverse x divided by 2. But we know that expression for the tan inverse x, and if we represent it and we get the final answer, that is 1 by 2 into x minus x cube by 3 plus x raised to 5 divided by 5 minus and so on. But this is the very most time notes. Whenever use the scientific calculator, so always we will use the radian mode. This is another question. Prove that tan inverse of x into 3 minus 4x square divided by under root 1 minus x square into 1 minus 4x square is equal 3 times x plus x raised to cube divided by 6 plus 3 times x raised to 5 divided by 40 plus and so on. That is we want to prove that. So again same argument we will consider like the previous one. But here 1 minus x square is there when you can see the denominator of the question. So in that case 1 minus x is there, so we will use substitution x is equal sin theta or cos theta. So LHS is there. So here x is equal, that is the sine theta, so we can represent theta is equal sine inverse x. But if we put here all these value on the left hand side, so x is equal, that is the sine theta, and 3 minus 4x sine square theta divided by under root 1 minus sine square theta, and this is 1 minus 4 sine square theta. But after simplifying, we get here sin theta into 3 minus 4 sin square theta divided by 1 minus sin square, that is cos square, but under root is there, so it will be eliminated, so we get cos theta into 1 minus 4 into sin square theta can be written as 1 minus cos square theta. But after simplifying, we get this form. But this is what exactly our standard formula for the sin 3 theta and cos 3 theta. So here tan inverse of sin 3 theta divided by cos 3 theta, and that is what exactly tan 3 theta, and this is what exactly 3 into theta. But already we have considered theta is equal sin inverse x. That means x is equal sin theta, so theta can be written as sin inverse x. But we know that expression for the sin inverse x, and when we put all these values, so we get the final answer. So when we put theta is equal sin inverse x, and again we know that the sin inverse x is equal x plus x raised to cube divided by 6 plus 3 times x raised to 5 divided by 40 plus and so on. And after putting all this value, you will get the final answer. So in this video, we have discussed about the Maclaurin series based on the differentiation and integration method. Thank you for watching.